Hello everyone, welcome back to my YouTube channel. In this video I'll be solving a math problem which is an infinite series. Here it is. Cos theta plus sin theta, cos 2 theta plus sin squared theta by 2 factorial, cos 3 theta plus so and so and so till infinity. Here the pattern is cos theta plus, we have an introduction of sin term, then sin squared theta by 2 factorial, and the third term will be sin cube theta by 3 factorial. Here we have cos theta, cos 2 theta, cos 3 theta, so and so. In this type of problem, we use a method called C plus IS method. It's a very specific format in which cos and sin terms are repeated, and in this we utilize imaginary numbers. Here I is the square root of -1, and you'll see why this is called so in a minute. Yeah. Now the way to solve this is we will try to make two separate series, one involving mainly cos and one involving mainly sin. Here there's the main term is cos theta, cos 2 theta, cos. This pattern we'll maintain with cos. So essentially for the first series we'll call it C. We'll write the same thing and you'll see the difference in a bit. That's the same series. Now we let another series S be equal to same thing as this, but with this pattern, this cos term changed to sin theta plus, but we keep this the same because we want to be able to factorize that bit out when we kind of add these two, and you'll see why. Plus sin theta, we keep this the same, change this to sin 2 theta plus, keep this the same, times change this sin 3 theta plus so and so to infinity. Now we have two different series. Now let's multiply all terms of this series by the unit of the imaginary unit, that is I, square root of -1. So if we multiply by I, at every term we'll get series like this. Now we'll use a very interesting fact which is called Euler's formula, that is e raised to I theta is equal to cos theta plus I sin theta. So if we have cos theta plus I sin theta, we can write it as e plus I theta. We will be utilizing this fact when we add these two equations. So C plus IS. This is where the method gets its name from. So these type of series are called C plus IS series, and it's called the C plus IS method. So here cos theta, so C plus IS, add each corresponding term, cos theta plus I sin theta, and since from Euler's identity we know that this is actually e raised to I theta. And here sin theta, cos 2 theta plus I sin theta, sin 2 theta. Here we can factorize sin theta out of this to get cos 2 theta plus I sin 2 theta inside. And this is why we need to keep this the same. And look, this will become exactly the same as this, but instead of theta it's 2 theta, so it will become e raised to I 2 theta. So here we write sin theta times e raised to I 2 theta. Similarly here we factorize the sin squared 2 theta by 2 factorial, and we get the same as this, but it's I 3 theta. Now you might notice the pattern that's going on here. Here there's e raised to I theta plus sin theta, e raised to I 2 theta, then sin squared theta by 2 factorial. So next here will be sin cube theta by 3 factorial times e raised to I 4 theta. Here we notice there's a common factor in all these, that's I, e raised to I theta. Let's factorize that out. We get this when divided by e raised to I theta will become e raised to I theta plus square to theta by 2 factorial e raised to I 2 theta plus so and so, till infinity. Now Now we have a very interesting pattern here. If you let this term be equal to x, suppose, this whole series will look something like 1 plus x plus, look, here if you square this you get sine squared theta e raised to 2y theta, and that's exactly this. So we get x squared by 2 factorial. So next terms will be x cubed by 3 factorial and so on. This is a very specific type of series, and this is called the Taylor series for the function e raised to x. So whatever x is, if it appears in the series, the whole thing will, the whole infinite series will equal e raised to x. So we can actually utilize this and write this as e raised to I theta times e raised to x, which is sine theta, e raised to I theta. So we actually have an exponential inside an exponential. Now for now, let's the first steps. So we have c plus is equals e raised to I theta times e raised to sine theta, e raised to I theta. Now note that what we're trying to find is the series which is equal to c. So we're trying to solve for c in this. Let's see how we can do that. Now here we have e raised to sine theta, e raised to I theta, and we know that from Euler's formula e raised to I theta is equal to cosine theta plus I sine theta. So we can put that in there. So I theta times e raised to sine theta times cosine theta plus I sine theta. And now let's just expand this. E raised to I theta times e raised to sine theta cos theta plus I sine theta times sine theta, that's sine squared theta. Now here we can, since this is an exponent and the exponents are added, we can separate it by multiplication. E raised to sine theta cos theta times e raised to I sine squared theta. Now look, we have common I exponent here and here. We can add only that. So let's write this term first, times e raised to I, take the I common, theta plus sine squared theta. So we will get c plus is as e raised to sine theta cos theta times e raised to I theta plus sine squared theta. And this is again in this form. Instead of theta, we have theta plus sine squared theta. So we can write this as e raised to sine theta cos theta times cosine of theta plus sine squared theta plus I sine of theta plus cos squared theta. This will be, we can expand this obviously, but now let's get to the whole point of this. Now this whole thing is a complex number in itself, and you can see the complex part of it, and this can be divided into two parts. It's a real part and imaginary part. For that we'll have to expand it, but we can just visualize it for now. So here, this term we multiply it to both these terms. So the real part of this will be e raised to sine theta cos theta times cos of theta plus sine squared theta. The imaginary part will be I e raised to sine theta cos theta sine of theta plus cos squared theta. And normally when we write imaginary part, we actually don't write I. So how to get in the imaginary number is the real part plus I times the imaginary part. That's the general form of a complex number. So here we have a real part is this and imaginary part is this. Now what are we trying to solve for? We're trying to solve for c, because we let this series equal to c at the beginning, and c is here the real term which is not associated with I. This term is however multiplied by I. That means that what we're trying to solve for, c is in fact equal to e raised to sine theta cos theta times cosine of theta plus sine squared theta. So that is the answer, the solution to this infinite series. So if we continue this summation till infinity, you will get this e raised to sine theta cos theta times cosine of theta plus sine squared theta. I think that's a pretty fantastic answer. So I hope you guys enjoyed this, and I'll see you next time.